Well, you guys, here we've come to the last class. And so I want to remind you about the final exam. Um, that is going to be on uh, Monday, beginning Monday. So Monday at 10:15 a.m. I will post that on the Blackboard site. And you can have 24 hours to work on that, although I don't really think it will require 24 hours, but you'll need to email that back to me by Tuesday at 10:15 a.m. Okay, so that is a period of 24 hours to work on it. Hopefully you'll need a lot less than that. And the rules for the final will be the same as the rules for the midterm. That is, you are allowed to use books, notes, websites. You are allowed to use computational software like Mathematica for doing integrals or whatever you need. You are not allowed to communicate with any people. So not with the current students, not with former students, not with faculty, not with your friends or relatives, not with any humans, okay? And so you have to be doing this on your own. And if I have any concerns about whether you did it on your own, I can ask you to explain your answers to me via Zoom after the exam. Okay, I think you're all graduate students in sciences, and you know how to do that sort of thing. Are there any questions about getting ready for the final? No. All right then. Well, for the last class today, what I wanted to talk about was just to briefly discuss smectic liquid crystals, just as another example of how we might use some of the same considerations about statistical mechanics and apply them to a different kind of system. So I'm going to give you a very brief survey of the concepts of smectic liquid crystals here. And, of course, feel free to ask any questions about this.
Jonathan,
Please, yes, Bajai.
I mean, in exam, you are going to ask questions from all the topics or after the midterms. I mean, if you ask,
All the topics.
okay, then what happens if you might repeat midterm questions?
I could, I might not. That's up to me, right?
Okay.
So, but yes, yes. Okay, good. Okay, so concerning smectic liquid crystals, right? And for the exam, of course, I posted some old exams on the website. And so you can all look at those. And that provides some sample of questions that could be asked. For smectic liquid crystals, right? So the idea here is that there is some partial positional order because the molecules lie in layers. So to make kind of a rough sketch of that, people often will just draw the layers like this. So this is a picture of a system with layers. And what this means is each layer is full of molecules, right? So here are molecules. And here are more molecules. So there's no empty space between the layers, but the molecules are filling up the space. But if you look at a particular point on the molecules, that tends to define layers like this. And you might say then that this is a crystal in one dimension. So it's a crystal, say, in the z direction, and it is a liquid in the x and y directions. So it's a crystal as you go from this layer to this layer to that layer. But within each layer, there is no crystalline order, right? So that within each layer, the positions of the molecules are random like a two-dimensional liquid. For that reason, we could classify the smectic liquid crystal, in comparison with the other phases that we've talked about this semester, in terms of order and symmetry. Okay, so if we think about what is the most symmetric versus the least symmetric, okay, we could say on the most symmetric side, we'll have a liquid because all the positions are equivalent and all the directions are equivalent. On the least symmetric side, you could have a crystal because there are both special positions and special directions. Now, somewhere in between, we have a pneumatic liquid crystal. It is less symmetric than the liquid because not all directions are the same. The pneumatic director is different from the other directions, but all positions are still the same. So in that respect, because all positions are the same, it does have some of the liquid's symmetry. For a smectic liquid crystal, it has to go between the pneumatic and the crystal. A smectic liquid crystal has special directions like the pneumatic, right? So not all directions are the same. A smectic liquid crystal also has special positions along the z-axis, right? That is, this value of z, where there's a layer, is different from this value of z, where there isn't a layer. Okay? So you don't have all positions equivalent to each other the way that you do in a pneumatic. So in that sense, this is less symmetric than a pneumatic. That is, as we go in this direction, we are breaking symmetry. That each of these stages, liquid to pneumatic, pneumatic to smectic, smectic to crystal, is breaking symmetry. It's taking directions or positions that were the same, that were equivalent to each other in a more symmetric phase, and is making them different from each other in the less symmetric phase. The breaking of symmetry is the same thing as increasing order. This way. And so we could say that this is the most ordered of the phases, and this is the least ordered of the phases. I think in one or two of the old final exams, I have questions where I make up some phase that maybe you haven't heard of before. And I say, is this phase more symmetric or less symmetric compared to the other phases on the list, right? So that might be a final exam question to think about. How to rank things based on what's more symmetric or what is more ordered, right? Recognizing that the ranking on symmetry is the opposite of the ranking on order. Okay, so coming back to thinking about smectics, right? So we would say, with each of these transitions where we break symmetry and go to a more ordered state, there's some kind of order parameter. And the order parameter tells you how much you're breaking the symmetry, and of all the possible positions or all the possible directions that could be selected as the special ones, which are being selected as the special ones. Okay? So for going from liquid to the pneumatic, we have the Q tensor as an order parameter that shows us how that orientational symmetry of the liquid is getting broken. For going from pneumatic to smectic, we need an order parameter that describes how the molecules are forming layers, right? And so it has to describe what's the onset of positional order, layer order in the liquid crystal. Okay. This is actually similar to what I told you about a couple months ago in terms of a crystal order parameter. This is like a mini simple version of the crystal order parameter, because here we only have layering in one direction, the Z direction, rather than in all three directions. So to give you that mini version, we could say when we form a smectic, we are forming a density wave as a function of Z. Okay, so here is Z, here is the density of molecules as a function of Z. In the pneumatic phase, this density is constant, right? It doesn't depend on position. So let's just call that some rho zero, independent of position. In the smectic phase, if there is strong smectic order, then what? Well, then we might have peaks just at specific values of Z. So if there's strong smectic order, we could have a peak like that at a certain position, and another peak, and another peak, and so forth, okay? And so this distance there is the smectic layer spacing. So the distance from one layer to another, the wavelength of the layered structure. So this picture is for strong Smectic order. That's what we might expect at a low temperature, so deep inside the Smectic phase. On the other hand, sometimes if we're just barely in the Smectic phase, then there might be weak Smectic order. That is, there could be a wave with just a small amplitude. So a wave that looks something like this. Okay. So here, I'll label this as weak Smectic order. Okay. So this would be just below the pneumatic to Smectic transition. So for this case of weak order, it looks like the wave is approximately a sine or cosine wave. So we might represent that as a density wave. Rho of z is the average density plus some periodic modulation of the density. So some rho of q times cosine qz plus phi, where q is a wave vector. So that is 2 pi over the layer spacing. So if you increase z by the layer spacing, okay, then you increase what's inside the cosine by 2 pi. And so you get back to the same value of the cosine, so the same density, right? That's what makes the density to be periodic. Now, this is very similar to what I showed you for crystals before. The difference from what I showed you with crystals is that for crystals, you have to be adding up a lot of q vectors in different directions, maybe in the x direction and the y direction and the z direction. In all the wave vectors on the reciprocal lattice associated with the crystal. Here it's actually simpler than that. You just have one q vector just in the z direction. Okay, so now the coefficient up in front, this thing represents the magnitude of the Smectic order. And this phi, this is a phase term, right? It's a phase, like you shift the phase of a sine wave to put the peaks at different places. And that tells you which values of z are the values of z where you get layers, right? So if phi equals 0, then the layers occur at z equals 0, and then z equals any integer multiple of the layer spacing. On the other hand, if phi is not equal to 0, then z equals 0 is not a peak. Then this whole pattern just gets shifted to the right or to the left by the phase phi. Now, it is conventional to combine the magnitude and the phase into one quantity. This works in the same way that I showed you in terms of crystals. So just as a reminder, we can work with a complex notation. So we could say there's the average density plus the real part of rho of q times the exponential of I qz plus phi. And then you can multiply out this complex exponential and rewrite it as rho q times e to the I phi multiplying e to the I qz. And then this combination of factors becomes a complex order parameter conventionally written as psi. Okay, so psi is this rho q e to the I phi. And so this is a complex number which includes both kinds of information about the magnitude and information about what is the phase of the order, not phase like pneumatic or smectic, but phase phi. So is the order, with positions here, or is it shifted upwards somewhere? And if phi changes as a function of position, then that could describe layers that are shifting as a function of position, maybe layers that are going up and down with a wave-like undulation. Right? So you could have a psi of x, y, and z that represents how the layer structure is varying as a function of position. It would be a complex field with this concept of a field that we've been talking about in this semester. And then people can develop a theory to describe the pneumatic to smectic transition. And that would mean a theory to describe the transition from psi equals 0, that's the pneumatic phase. Here, I should write it over here. That would mean the pneumatic is psi equals 0 to the smectic, where psi is not equal to 0. So there's been a lot of theoretical research on this over the years with different approaches, some of it with mean field theory, some of it going beyond mean field theory. One thing that makes the theory very rich is that the phases also have pneumatic order. You don't have just smectic order, but pneumatic order occurs on both sides of this transition. And it could be described by a Q-tensor if you care about both the magnitude and direction of the pneumatic order, or by just the director field N as a function of position, if you only care about the orientation of the pneumatic order, and you're going to assume that the magnitude of the pneumatic order is constant. And so now you have different order parameters which interact with each other. And a lot of theoretical work has gone into characterizing what is the relationship um, between nomadic and smectic order. Um, so this is something that we could talk about either in sort of a general conceptual way or in a more mathematical way. Right? So for a general conceptual approach, one way to look at it is just what's the relationship between the layers and the direction of the molecules. Right? So we could make a picture like this one, where we have layers in the xy plane, so that the layer normal is in the z direction. And then we could have molecules that tend on average to stand upright with respect to the layers, like this. Okay, so this means that the director associated with the molecules is in the z direction, and the layers are in the xy plane. Um, so the layer normal is also in the z direction. Okay? This thing is called the smectic A phase. So it is a subcategory of smectic phases. There can also be a possibility that these two vectors are not parallel to each other, but that they have some favorable tilt angle with respect to each other. So we could say, here are the layers, and maybe the molecular orientation is something like this. So here, the director N is pointing that way, and the layer normal is still in the z direction. Okay, and so this is another kind of phase that can form. This is a smectic C phase. Um, so here we would say that the molecules are tilted with respect to the layers. That's the common phrase to describe this. People call it molecular tilt. Of course, that's, if you hold the layers like that, then you say the molecules are tilted with respect to the layers. You could turn the picture over like that one, right? And then the molecules are pointing in the z direction and the layers are tilted. Of course, these two things are exactly the same. Those two things are exactly the same. It's just tilting my iPad one way or another. Or tilting the coordinate system in one way or another. But physically, there's no difference between saying the molecules are tilted with respect to the layers or the layers are tilted with respect to the molecules.
Excuse me, a
Uh-huh.
question.
Please.
I can see from the smectic C phase, each layer um, has a director, right? So is it possible uh, for for the director of one layer, um, which it, um, which becomes different from the director of the other layers. Um,
Yeah, that's an interesting research question, right? So that is what Cheng is asking, right? So is the director here going to be the same as the director in different layers? Or can you have a director that's well defined in each layer, but then it's random from one layer to another? Um, that's an interesting research question. Um, in general, the most common situation is to have the same orientation from one layer to the next to the next. Okay? There can be a more complex situation where it's alternating back and forth. Right, so going from one layer this way, the next one that way, the next one this way, the next one that way. Right?
good. Can you see energy difference between these two patterns?
Yes. So these things would be favorable in different kinds of materials. Right. So some materials would favor smectic C with a uniform tilt, and other materials would favor alternating tilt. Right? Um, and I let me postpone talking about that until I tell you one other thing. Okay. But can they be random? That was your original question. They're probably not. Probably there's going to be some correlation between them, but that is a subject between a subject of theoretical research. So it's maybe a little more than we can say right here. Okay. So the the point is you can get a whole bunch of different kinds of phases. And so there's a real collection of many kinds of smectic phases. So here I am showing you two of the smectic phases, smectic A and smectic C, but there could be other varieties based on what's the pattern of molecular tilt. Is it uniform? Is it alternating, like this picture? Is it some even more complicated pattern of alternation where, it has a periodicity of 3 layers or 4 layers or something? All kinds of weird things happen. There's a huge collection of different sorts of behavior that has been observed experimentally, and there are lots of theoretical models to investigate that sort of thing. And then there are even more varieties of smectic phases based on not the molecular tilt, but on other kinds of orientational order within the plane. So for example, sometimes the molecules are not just shaped like cylinders, but the molecules might have some cross section that's more like a rectangle. And then you could say, well, for the rectangles, if I look at them this way, maybe here's one, and then here's another one. And you get some interesting alternation of the orientation of all of those rectangles. That is called herringbone order. Herringbone order. Or I spoke with some of you about hexatic order after class recently. And so sometimes there could be hexatic order within any one of these smectic layer planes. Okay. Now, the last complication that I want to add to this mix, which is also a big area of liquid crystal research, is chirality. That is the difference between right and left-handed forms of molecules, which I spoke about in the context of cholesteric liquid crystals and blue phases in the last class. Okay, so what if we have a smectic phase with chirality? Okay, so this adds a couple of special interesting effects. One effect is ferroelectricity. So this is something which arises from interesting combination of symmetries in smectic liquid crystals. So suppose you have a smectic liquid crystal and it is tilted. Okay, so you have tilt, it's a smectic C phase, and you have chirality. Let's take our picture and try to see what happens if the molecules are chiral. Okay, and we get an interesting point, which I can try to illustrate to you with a cartoon. Okay, so here's my cartoon. Let's draw each molecule as if it were a fish. Okay, there is a particular kind of fish in the ocean, which has both of its eyes on one side and no eyes on the other side. I think these are fish which have evolved to lie on the ocean floor. And so they have both eyes sticking up into the water and no eyes sticking down into the dirt. Okay, so let me try to draw one of these fish. Okay, here's a fish with two eyes on one side, like that. Okay, suppose you have molecules that look like that. Okay, so that's kind of a cartoon of a chiral molecule. Now, I want to make a smectic phase of such chiral molecules. Okay, so I'm going to make smectic layers. And let me see if I can actually do this with my lasso. So if I copy this, okay, and now I want to paste a whole bunch of these fish. Okay, so I'm going to paste it. And let's say it's tilted, so it has some position like this one. Okay, now let me copy a whole bunch more of these guys. No, I want to copy it again. The same orientation. Copy, paste, paste, paste. Okay, we have a whole bunch of fish like this in the smectic layers. Okay, and then it still has pneumatic order in the sense that half the fish are pointing up and half the fish are pointing down. Okay, so let me now draw some of them pointing down. I could rotate it around like this. Okay, here are some fish pointing down. Uh-oh, there it is. Okay, so if I copy some more of these guys, copy, paste. Uh-oh, I copied and pasted too much. Let's try that one again. Copy. Oh, maybe it's because it's connected. That's my trouble. Huh. You would think I would understand how to use this software by the end of the semester. Okay, let's try one more time. All right, here you have a smectic C phase of these chiral fish. All right, now suppose each fish has an electric dipole moment. Could happen, why not? Molecules have electric dipole moments. So let's think about the electric dipole moment, which might be in any arbitrary direction with respect to the fish. Okay? If it has some component along the long axis of the fish, a component pointing this way, well, that's going to cancel out because half of them are pointing up and half of them are pointing down. So there's no dipole moment like that, right? On a statistical average adding up over all the fish. Likewise, there might be a component pointing, from the belly to the back of the fish. That also will cancel out. Some of the fish are pointing up this way, some of the fish are pointing down that way. So there's no net electrostatic polarization that way. Right? But now, suppose that there is a component of the electric dipole moment from the back to the front of this picture. Okay, so it's like a vector pointing out at us, out of the screen. A vector from the side of the fish with no eyes to the side of the fish with two eyes. That component just adds up. It's pointing in the same direction for all of these fish. So that means that this phase, with the combination of tilt and chirality, can have an electric dipole moment pointing out of the plane. An electric polarization, P, out of the plane. This was a prediction based on symmetry by Robert Meyer, although he did the symmetry in a somewhat more formal way. The picture with the fish was first made by Pierre-Gilles Dejean. And anyway, it really happens, right? And so if people experimentally make liquid crystals with tilt and chirality, that is, they make a smectic C phase of chiral molecules, they really can observe an electric polarization. And this electric polarization couples with any electric field that people apply to the materials. So it is a way of making a different kind of electro-optics than the usual pneumatic liquid crystal. And so this is an interesting illustration where this symmetry consideration really does show up in experiments, and it may have some important applications. Okay, so that's ferroelectricity. Okay, and one reason why I wanted to mention that is that if this is coming back to Cheng's question from a few minutes ago, if you have smectic C order that is the same from layer to layer to layer, that makes a ferroelectric phase. If you have a smectic C phase where the orientation is switching back and forth from layer to layer, right, where there are two possible orientations, and it goes back and forth between them. The word for that is, if this happens in a chiral liquid crystal, the word for that would be antiferroelectric. And so that is the word that I was trying to use a few minutes ago, but I had to say this thing about chirality first before I got to that. Then the more complicated structures with multi-layer periods are called ferroelectric. Ibrahim, you had a question?
Yeah, yeah. So we know that chirality has more than one type, like planar chirality, axial, helical, or central chirality. So here, this associated ferroelectric effect is associated with certain type of chirality or all these different types.
It would be associated with any type of chirality.
Yes.
It would normally be associated with a permanent chirality that is created by the chemist who synthesizes the liquid.
Central one.
Right. As opposed to a chirality that is free to switch back and forth dynamically.
Yeah.
But there are liquid crystals, especially bent core liquid crystals, that have chirality that is free to switch back and forth dynamically. And then those materials also make smectic phases. And there's a huge range of behavior that occurs there. And that's a great research topic, which I don't have time to talk about here.
Yeah, thank you.
So this is the first thing I wanted to say, the ferroelectricity, and Professor Yockley has a way that he likes to refer to that, which is that the combination of tilt and chirality makes polarity. Right, that's something he likes to talk about. There's another version of that, I'll call that effect 1B, which is the electroclinic effect, where Professor Yockley's way of describing that is chirality and polarity makes tilt. That is, if you start with a smectic A phase of chiral molecules, and then you apply an electric field, you can induce tilt. Okay, and so that's the origin of this word electroclinic, right? So this electro is the stimulus, it's an electrical stimulus, and you get a clinic, you get an incline, which is a tilt. Okay, so that's one thing to mention. The last thing that I want to mention before I totally run out of time is a different effect of chirality. Another effect of chirality is that you tend to get a twist in the director field. But there's a problem, okay? So you might say the problem is, well, the director field has two considerations, right? It tends to twist, and it tends to align along the smectic layer normal. So for a smectic A phase, it tends to align perpendicular to the layers. For a smectic C phase, it tends to align at a particular angle with respect to the smectic layers. Okay, so the director has two tendencies like this. That is to say, the free energy is minimum if the director does both of these things. If the director twists and the director aligns along the smectic layer normal. The problem is that it cannot do both of these things at the same time, that the geometry just doesn't work. If you try to have a director along the smectic layer normal and you try to twist the director like a cholesteric liquid crystal, you would have to tear the smectic layers. It doesn't work if you have smectic layers that are just nicely connected together. So those two things together make a kind of frustration. That is, it cannot do both of those things at the same time. So the material needs to make some compromise between those two tendencies. Okay? Now, it might just give up on the smectic order and just make a cholesteric liquid crystal or a blue phase. It might give up on the twist and just make a regular smectic liquid crystal with no twist. Or, under some circumstances, it can make an interesting compromise phase, which is called the twist grain boundary phase, or TGB. And this is a complicated thing which I cannot draw, so I just made a picture in Mathematica over here. The idea here is that you have a slab of smectic order. Okay, so right over here is smectic order, which has a nice, well-defined layered normal. So the molecules are aligned perpendicular to the layers, coming up like that. And then there's a grain boundary. There's a boundary in here where the smectic layers get disrupted, and then they form again over there with a different angle. And then another boundary here, and then another slab of smectic order there. And so this whole thing repeats periodically. And so it gives a kind of a twist. It gives a twist of the director field along this axis, right? As you move along this axis, perpendicular to the grain boundaries, the director is twisting from one orientation over here to another orientation there, there. Okay, so it is a global chiral structure, but it is not twisted everywhere. It has some untwisted region and then a lot of twist inside the boundary. And then another big untwisted region, and then some concentrated twist, and so forth. And that repeats periodically. So that is a very complex structure, but it has been identified in experiments. And so this is an interesting kind of compromise that can come from the combination of different sorts of order, the nematic order and smectic order and chirality. And so, this gives, maybe one aspect of liquid crystal research that I will leave you with. Some liquid crystal research which involves figuring out how all these different kinds of order parameters can interact with each other, and how they can make complex structures, which we can study theoretically and explore in the laboratory. and in many cases can actually utilize for some technological applications. Well, at this point, there are all kinds of other things that we could talk about, but I have run out of semester. So I will leave you guys with this point, and I will wish you well for the rest of graduate school and hope you all stay in touch and let me know about the great things that you all do. For now, I will stop and I'll be glad to answer questions about Smectics or about anything else in the semester. And then don't forget about the final exam on Monday.